All right, so this is Foundations of Math 30, and this is going to be a lesson for 5.6. As I just mentioned, I teach 5.6 from the textbook here, and this is, of course, Foundations of Mathematics 12 textbook by Nelson, and I teach 5.6 before I teach 5.5, so a little note there. All right, so let's talk about independent and dependent events, okay? We need to know the difference between those two, and we need to know that well in order to tackle some of this, some of the math a little bit later. So an independent event, these are two or more different events that occur in which their outcomes do not depend on each other. So they're totally separate. An example would be, and I've crudely drawn here, two coins, okay? Oh, it's frozen? There you go, frozen, unfrozen. Thaw that out. So two coins. Now, if I flip two coins even at the exact same time, one coin does not care what the other coin turned out to be. It doesn't matter, right? They're completely independent. So it would be like, you know, your decision on how many hours to study for math versus your decision to go play video games. Now, you might say, hey, I actually might play video games a little bit more if I didn't have a math test coming up. Oh, okay. So then the amount of time you'd spend studying maybe depends on the amount of time that you do another activity, or I should say the amount of time you play video games depends on the amount of time you need to study, because that would be priority. So that would be dependent, all right? So there's an example where those two events might be connected to one another. As one goes up, the other goes down, or something like that. So that's a dependent. Those are dependent events. The probability of one event occurring depends upon the outcome of another event. So I've also crudely drawn a pair of pants and a t-shirt, whatever. And you may think, well, you know what? There are certain shirts that I would never wear with certain sets of pants. Maybe the colors don't go, or maybe whatever. I don't really know. I'm not really a fashion guy, so I don't really know. But this might be, the probability that you would wear, you know, a certain type of shirt might depend on, you know, what happens with the bottom. They might be connected, so they might be like dependent events, okay? So if you're wearing blue pants, let's say, you might say to yourself, well, I'm not going to wear my red shirt with my blue pants. So I take away some of my options right away. And that's conditional probability. That's dependent events, okay? They depend. So do you guys get the contrast there? Okay, independent, two coins being flipped, versus dependent events might be, you know, what you choose to wear, top with bottom. It depends on the color and the style and everything, okay, or the weather or whatever. So dependent events there. All right. Okay, so how does that affect things? Well, think about independent events. If we are talking about the probability of two independent events happening at the same time, this is exactly what we've been doing in the first part of this chapter and in last chapter when we're talking about fundamental counting principle, right? So you have two events happening, and what are the number of choices for this event and the number of choices for this one? You multiply them together, and that's how many different ways that you could do those two things at the same time. So same thing, independent events. If we have a probability of one event happening, A, so this is probability now. If the probability that this event happens, so let's say I flip a coin, so the probability of getting a head would be 1 out of 2, and I flip another coin, with the probability of getting another head would be 1 out of 2, let's say. Those are independent, so you would simply multiply those together. The chance of you getting a head and a head when you flip two coins would be 1 out of 4, because each of them are 1 out of 2. So you multiply those, 1 times 1, 2 times 2, that's 1 out of 4. And of course, with our coin example, that's exactly what it would be. So here's the heads and heads. You could have heads, tails, you could have tails, heads, and you could have tails, tails. Blech. So tails, I wrote H. Tails, tails. So, right? Probability of heads, 1 out of 2. Probability of heads again, 1 out of 2. Multiply those, you get 1 out of 4. There it is, 1 out of all 4. So independent events are multiplied. So that's the and down here. It's So that's and, right? Ahead and ahead. So those are where we multiply this right here, PA times PB. Okay, okay. Now there are OR events as well. So OR events. OR events. So what are the chances if I flip coins, what are the chances of me getting a head or a tail, let's say? Or what's the probability that I would get a head or tail that's well, a head. Let's take a different example. What's the probability that it will rain today, or the probability that you will attend math class? Well, those would be two separate things. And if we're talking about OR, what do we normally do with OR events? When we're trying to find either the number of events, or in this case, the probability, what do you think we should do? As opposed to multiplying, what do we do with OR? Add, right, add. Okay, so we'll add. Okay. And so if we're talking about independent events and we're trying to do OR, this is like two separate circles in the Venn diagram, right? They're mutually exclusive events, and think about it that way too. They're separate, they're independent, okay? You can just add them. Okay, so OR events we can add, and events we can multiply. So, all right, are you following me so far? This still holds true from what we've learned before, OR and AND. All right, let's take a look at example 1 from our textbook. This helps us a little bit, and for this question, I'm going to draw a tree diagram. So I want you to pay close attention. You can also follow along in your textbook. If you have your textbook with you, this example 1's on page 355. Page 355. Okay. All right. Mokhtar and Chantel are playing a die and coin game. Each turn consists of rolling a regular die, so it's 6-sided, and tossing a coin. So we've got rolling a die and tossing a coin. Okay. Points are awarded for rolling a 6 on the die and or tossing heads on the coin. So here's how the points break down. Now, first of all, are these independent events? It says they are, but are they? If you roll a die and then you flip a coin, does the outcome of the coin flip depend upon what you got with the roll of the die? Are they dependent on each other, or would they be totally separate? They're totally separate, right? The coin flip does not care what you got on the die. They're totally separate. There's nothing influencing the other. Okay. So how does this break down? 1 point for either outcome. Okay. So that would be like I have kind of written down here as in part of my solution already. That's the OR, a 6 or a head for either outcome. Does that make sense? Okay. 3 points for both outcomes. Well, that's like rolling a 6 and flipping a head. Okay. For both, that's and. And 0 points for neither. So neither outcome, you get 0 points. So players alternate turns. The first player who gets the 10 points wins. This is a game that you guys could play, right? We can actually play this game. We won't today. But it says determine the probability that Mokhtar will get 1, 3, or 0 points on his first turn. Okay? 1, 0, 3, or 0. Which one would he get? Okay, well, this is a bit of a tricky question here if you think about it, but let's do a tree diagram to maybe try and simplify it a bit. So if you remember the tree diagrams, if you have two events happening, sort of one section of the tree diagram would be one event, and the next section of the tree diagram would be the other event. So let's say that the probability on this one, the probability of rolling a 6, okay, is one option. Now, you might think, well, isn't there 6 options? Like, aren't there 6? Well, we're going to do probability of 6 and then probability of not 6. Okay, so all of the rest of the options are going to be on the second branch. We're going to do it like that. Okay, so let's do a tree diagram. And with this tree diagram, we're going to assign our probabilities on the actual branches. So just kind of wait and watch, and this is how this is going to work. This is gonna be a real good way to do these, I think. Okay, so that's that's a die, so it's rolling a die. Okay. Now tossing the coin is going to be the second part here. And for each, so if I get a 6, I could then get a head, so probability of a head. And this one would be the tails. That would represent the probability of rolling a tail. Okay. And then I'm going to put lines here for these outcomes, for all these outcomes. Over here, if you don't roll a 6, you could still roll a head, right? If you get an or. So roll a head, flip a head. So probability of a head here and probability of tails here. And then your outcomes there. All right. So this is the probability here of a 6 and a head. That's what this line represents, this space right here. This second space is probability of a 6 and a tail. Okay. Here, probability of not a 6 and a head, and probability of not a 6 and not a head. And I'm going to write them like that. So hopefully you should be comfortable with this notation, right? Should be comfortable with the whole complement notation there. Okay. Now, what about the probabilities here? Okay, so let's assign these probabilities. What's the probability of rolling a 6? That's the first thing we're going to do. What's the probability of rolling a 6? There's one option out of how many? Yeah, 1/6. So 1/6. That is the probability of getting a 6. The probability of not getting a 6 would be 5 out of 6. Let me just rewrite that because it's hardly readable. I'm going to do 1 out of 6. I'm going to do it right there. Now the probability of flipping a coin and getting a head is 1 out of 2. Probability of getting a tail is 1 out of 2. 1 out of 2 here. 1 out of 2 here. Okay? You guys with me so far? Is this making sense? So what we can figure out here then is we can figure out the probability of getting a 6 and a head. And that would be, because they're independent events, we simply multiply 1/6 times 1/2 to get 1 out of 12. Okay? So there would be 12 total outcomes. Now we don't need to show all of the 12 outcomes, right? We don't need to show that because we're only considering a 6 and one of the coin flips and a non-6 and one of the coin flips. So we really only have 2 branches here instead of 6. And I mentioned that before. So but there'll be 12 total outcomes, looks like. Okay, what about a 6 and a tail? Well, that's the same thing. All right. What about a non-6 and a head? Well, that's going to be equal to 5 over 6 times 1/2. That's going to be 5 out of 12. So the probability of getting not a 6 with a head is much bigger than getting these other 2 ones so far. It makes sense. And not a 6 and not a head, well, it's the same thing. It's going to be 5 out of 12. It's 5/6 times 1/2. All right. So now we're ready to go with trying to figure out the points here. So 1 point for, let's do 3 points for both outcomes. So where does he get 3 points here from? Oops, wrong pen. So 3 points comes from a 6 and a head, right? That's this one. So what are the chances? 1 out of 12. Okay, you good with that? So that's the both outcomes. So the probability, let's do this. The probability of a 6, probability of 3 points, let's do that. Probability of 3 points is 1 out of 12. Because that's where you get a 6 and a head. Okay? The probability of, let's do neither outcome here. Neither one. Which one is neither? That's neither a 6 nor a head. Well, if you look on your tree diagram, it's pretty easy to see that path. That's why I like the tree diagram so much. So that path is not 6 and tail. So guess what? That is 5 out of 12. You see that? So neither outcome, the probability of 0 points is 5 out of 12. Okay. Now, the probability of rolling a 6 or a flip ahead. Okay. So this is where it gets tricky, because we have to look at our tree diagram here, and this one includes rolling a 6, right? Both of these two here. And or flipping ahead, well, here's a head and here's a head. Okay. And I could write this non-head as a tail there too. I could do that too. That's a tail. Okay. So what do I do? Well, the probability of getting, was that 2 points for that middle one? Well, 1 point for either. Of 1 point is going to be, so I have a 6 here and a 6 here. So that's 1/12 plus 1/12. Because it's or now, right? Or. So it's the first one or the second one. And then probability of heads as well. So I have to consider the heads as well. So there's this one, 5 over 12. Okay, I could get a head there. All right. But this one over here, I've already counted, haven't I? So I could get a 6 for this one, 6 for this one, and a head for this one. So I have to be careful here. So the probability of 1 point. So he would get 1 point here, right? He would get 1 point here and 1 point here. But this 6 and a head, that's actually the 3.1. So we have to subtract the 1 out of 12 there. We have to subtract this one because this one's already a 3-pointer. Okay? So I'm getting around to this, but so this is a 3-pointer, and then these are, this one and this one are the 1-pointers. Okay? 1 point, 1 point. So I've counted this one, this 3-point, twice really in my points. So I gotta get rid of one of those. So the probability of 1 point is 1/12 plus 5/12, or 6/12, or the probability is 1/2. Okay? So here are our probabilities there for this question. Now you can kind of see how drawing a tree diagram, okay, to be able to see this all in one spot in one diagram is going to be helpful. Because for you to kind of remember all of these numbers and which ones you've already counted and blah, 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 it's going to be tricky. So I would strongly encourage a tree diagram there. Okay? So and is multiply, or is add. Okay? I will mention something else that you will come across. You will come across this. Okay? So in drawing cards, okay? If you draw 2 cards from a deck, and after you draw the first one, you put it back, your second draw, or those 2 events, would be independent. Okay? So this is the example up on the top here. I draw a card, I look at it, and then I put it back in the pile, in the deck, and I shuffle and I draw again. So that second draw doesn't depend on what happened to the first draw because it's all been erased. It's been replaced, you see? But if, and again, this will show up in some of your questions in your assignment and stuff. This will come up, so I'm trying to help you now. So drawing 2 cards without replacement means that we have a deck of cards, you pull a card out, and then you put it aside. Now for the second draw, well, the game is totally changed now, isn't it? The second draw. So you're pulling 1 out of 51 now, see? Okay? Or think about this. I have 52 chances to pick a card at the first pick, and then because I didn't replace it, I now only have 51. So this is dependent, okay? And you're gonna have some questions sort of like that. All right, so that concludes part A of 5.6 video. We are going to finish this 5.6 in the second video, so watch that video for the rest of 5.6.